to them.
Okay, thank you so much. It's great to be here. And yes, we'll be talking about tackling challenges of distributed deep learning with open source solutions. So just to quickly set the agenda, so first we would like to describe the problems that we have noticed with practical deep learning, and then present what we believe is the best solution to those problems, Ray AI Runtime, also known as Ray Air. Quickly showcase that library, then go a bit more in depth why we believe that it is the best solution, and finally go on a deep dive at all the different components that make up Ray Air. So yes, let's start with the problems with practical deep learning. Let's set some context here. As anyone who has worked with deep learning models in production can attest, there are many problems that stem from the ever-increasing data and model sizes. So first of all, obviously, training takes too long. The computational requirements are only growing. The number of parameters is only growing. The amount of data is also starting to reach sizes unknown before, to the point that it is not really practical to train deep learning models on one node anymore. And finally, the models themselves are also growing in size, to the point that one device, one node cannot fit them all in a memory. So obviously, the solution to that, if we cannot fit a model or our data on one node, we have to go distributed. We have to scale it up. So we do that, and now we notice a bunch of new problems. Now that we have gone beyond a single node, the developer velocity drops down dramatically. The complexity of our code starts increasing now that we have to think about things like fault tolerance, about distributed checkpointing, about synchronizing parameters. We also start to have to learn how to do DevOps. We have to start to learn how to manage complex infrastructure, how to set up different clusters, how to use different cloud providers. And finally, even though we may successfully scale up our training, it is not enough just to scale up our training. In production, we'll have to scale up the entire ML pipeline, from data ingest through training, through hyperparameter tuning to serving. So how do we fix the problem? So let's for a moment imagine an ideal solution. It would be a tool that we can easily onboard onto. We don't want to waste any time learning new complicated APIs. We want to pick it up and start going with it right away. We want a tool that abstracts away the infrastructure. We don't want to have to learn how to deal with all those different node types, how to deal with starting up clusters, how to deal with resource utilization. We just want to focus on what is most important for us, which is training the model. We want to have something that will give us extremely fast iteration speed. We don't want to waste time on node startup. We don't want to waste time on anything that is unnecessary. We want to be able to avoid vendor lock-in. We want to be able to use GPUs and other resources from any cloud provider, so that we can, for example, integrate with our existing systems or pick the best solution, the best price point for our needs. And finally, we want that tool to integrate well in an end-to-end machine learning platform, from data ingest to model serving. So when we look at existing deep learning frameworks, we can broadly categorize them into two groups. So on the one side, we have the lightweight frameworks. So for example, PyTorch Lightning, Keras. So they are very easy to pick up. They are very easy to learn. They have simple APIs. They are quick to iterate on. But when we try to scale them up, we see that they have not really been designed to do that. Putting them into production means more complexity and more work required on our part. So we can instead choose the heavyweights. So for example, the closed source platforms like Vertex AI. They are production ready. They are robust. They are what we would gravitate towards when we want to do some serious serving, serious inference. But we start seeing that they are quite inflexible, quite hard to customize. Working with them often means that we have to learn completely new concepts, completely new APIs. We would like to stay in Python land, but that is often not possible. So we have been working on Ray AI runtime, and we believe that it is able to combine both the nimbleness of the lightweight frameworks with robustness and production readiness of the heavyweight frameworks. So let's quickly dive into what is Ray Air in the first place. So Ray AI runtime, is an open source toolkit for building end-to-end machine learning applications. So we are taking advantage of the rich Ray machine learning ecosystem and all the different libraries that have been building over the years, and we are combining them into one unified API that is able to effortlessly scale. But why are we building on top of Ray in the first place? So if you have attended Jules' talk before, you may know, but Ray is an open source library that provides simple, universal APIs for building distributed applications. And that gives us, Ray gives us several advantages that we can immediately use. So first of all, Ray provides an efficient data layer and distributed object store, which allows us to, for example, avoid unnecessary memory usage. And that, in turn, allows us to take advantage of scalable data ingestion. Ray is completely Pythonic. It has a completely, Python is a first-class citizen, and the API is completely Python-based, which means that it is extremely easy to pick up, extremely easy to iterate on and distribute. And finally, Ray provides robust scheduling and resource management through Ray Core and Ray Autoscaler, which means that the hardships of process orchestration and fault tolerance are abstracted from us. So in short, Ray provides solutions for the challenges of distributed computing. There are many companies and users using Ray. I will not go into detail about their use cases, but if you are interested, please visit ray.io to learn about their journeys with Ray.
Cool, yeah, so now we have an overview about what Ray Air is. Let's go into more details about why we think it's the best solution for distributed deep learning. So again, like just recapping, how do we fix the problems, right? Like we want to be able to easily onboard onto this toolkit. We don't want to change our code a lot when we're going from deep learning on a single thread in a single threaded setting when you go distributed. We want to abstract away all of our infrastructure, right? So as a data scientist or ML engineer, I don't want to be thinking about resources, scheduling, process management, things like that. I just want to build my model. I want to be able to use GPUs from multiple cloud providers, and I want to be able to iterate quickly, right? That's the nature of deep learning work. Lots of experimentation, lots of trying stuff out. I need to make sure I can do that very quickly. And as Anthony mentioned, finally, we need to integrate well with an end-to-end ML platform and make sure every component is scalable. So Ray Air meets all of the requirements. It's very easy to use and iterate. It abstracts away the infrastructure, and through all the libraries, the Ray libraries as well as integrations with other open source machine learning libraries, you can easily build an end-to-end ML application or end-to-end ML platform with Ray Air and its integrations. So before we dive in specifically, let's just take a look at what some users are saying. So you saw in the previous talk, right, Lyft is using Ray for some of its machine learning work. Here's another user who, an ML engineer from a large music streaming company who's been trying out Ray Air, and they've really seen that it's helped them with their developer productivity. Right, they can create these end-to-end machine learning pipelines within a few days. They can easily extend the code in Ray Air to add any custom logic that they want because it's all in Python. It's very customizable, very flexible. And finally, it's able to unlock complex features, allow them to do training at scale very easily. So let's take a closer look at the various components in Ray Air. So the first one, like we talked about, is very easy to onboard onto, right? So the goal here is that, you don't have to change your code at all when you want to scale it out, right? So you can take any example, PyTorch example, TensorFlow example, get that working on your laptop, get that working on a single GPU on Google Colab. But then now when you want to scale it out to a multi-node cluster across multiple GPUs, it's very easy to do so. So it's just 3 steps here. The first is that you put your training code, the standard PyTorch training code, into a single function. Then you wrap your model and data set using the utilities that Ray Air provides. So this prepares your model. So when you do train.torch.prepare model, this prepares your model for distributed training. And finally, you create your Ray trainer. So in this case, we're going to be using a torch trainer. You pass in the function that you defined, and then all you have to do is specify a scaling config here. So here we want to scale, use 4 workers to scale our training. And then just like that, you can just do trainer.fit, again, completely all in Python, and now you can run your scaling, run your training at scale. So Ray Air also abstracts away the infrastructure. So Ray comes built in with the cluster launcher, allowing you to easily spin up clusters on AWS or GCP or other cloud providers. And then once you can do that, you can take the same script that we saw and then submit it as a job. Or for interactive development, you can actually continue to use notebooks and connect that to your Ray cluster. So you can have all the resources available in a large cluster, but still continue to develop using notebooks or your favorite IDEs, for example. And when it comes to scaling your workload, very easy, right? It's like all you have to do is, I have scaling config. I have 1 worker. Just change that to 100, set use GPU to true, and that's it. Now I'm like scaling across hundreds of GPUs. The rest of my code does not have to change at all. So I can easily move between a laptop to a cluster, move between CPU to GPU, from an undistributed setting to a distributed setting, just with like a few lines of code change. So just taking a look at like how these Ray Air trainers work underneath the hood. This is just standard data parallel training that we have. So Ray will launch multiple processes across your entire cluster. Each process, if you have GPU enabled, each process will be on 1 GPU, and will load a model replica on that GPU. And when you pass in a Ray dataset to this trainer, it'll automatically shard this dataset for you, do any pre-processing if you have that specified, and split the dataset so that each training worker will be training over 1 shard of data. And then after every batch of training, the weights across all the training workers are synchronized. So this essentially allows you, through data parallel training, you can train on the same amount of time it would take you to train on 1 batch of data. In the single-threaded case, if you're using 4 workers, now you can train on 4 batches of data. Another benefit with using Ray and Ray Air here is extremely fast iteration speed, right? So, most people, when they're doing model development, like you want to stay fully into Python, right? You don't want to mess around with like, Kubernetes. You don't want to have to package your code in like a Docker image and republish that on every single change you make. So with the Ray, you can do this entirely and develop with Python at scale, right? So you have your Python script, you can run it on your cluster, and then if you want to make a change, you just change your script, and you can immediately run your code after any changes. So if you take a look at this chart, like just comparing like the iteration time when using Ray Air versus SageMaker, with SageMaker, you have to spin up a VM every single iteration, right? It just makes the whole developer experience like very, very annoying, very frustrating. But with Ray Air, it's not the case. You just treat it as you would like developing in your laptop, except you have the resources from your entire cluster. What this also means is that you have very low friction when you're going from development to production, right? Because you're developing at scale, now you know when you actually want to take this and move it to production, the scale is not a concern, right? You've already confirmed that during the development process that this thing works at scale. And the last benefit that we have here is like cost effectiveness, right? So how can we leverage GPUs efficiently? Part of this is that you want to be able to use any cloud provider. You don't want to be locked into a specific one. For example, if you have credits on AWS, credits on GCP, you want to be able to easily switch your workload from one cloud provider to another without having to make any changes. Right? So Ray supports any cloud provider. The other part of this is supporting spot instances. Right? So this is where like Ray Air's fault tolerance comes into play. Right? You can use the cheaper spot instances. And even if the nodes go down, because of the checkpointing mechanisms that are provided in Ray Air, you can continue training from your last checkpoint. You don't have to restart your training job from the beginning. So just an example of how this fault tolerance works, right? If you say you have 4 workers you're training with, one of these goes down, so you have a spot instance, the node gets preempted. Because you have checkpointing enabled, the Ray autoscaler will automatically spin up a new node for you, and then you can continue training from the last checkpoint, and then resume from that checkpoint. So no need to restart training from the beginning. And as we all know, like training is never done in a vacuum, right? Like, all these other talks here have talked about, the feature processing, data ingestion, all the upstream tasks to go into training. And then after your training, once you've trained your model, right, how you can serve it, how you can do inference and prediction and evaluation on that model, right? So you have to make sure that the toolkit that you choose, the framework that you choose for training can very easily integrate with the ones that you want to use for data ingestion, as well as the ones you want to use for hyperparameter tuning or model serving. So in addition to like the training libraries that Ray Air provides, there's also Ray datasets for last mile preprocessing and ingestion into training, Ray Tune for hyperparameter tuning, and then Ray Serve for model serving and composition, as well as a whole bunch of open source ML ecosystem libraries that work very seamlessly with Ray Air, right? So if you're using Hugging Face, if you're using PyTorch Lightning, if you're using Horovod, you can easily scale those with Ray Air. You can switch from PyTorch to TensorFlow without having to change the APIs that you're using. And then we also integrate well with like the monitoring tools like MLflow or weights and biases and TensorBoard. So here's just like an overview of the full ecosystem around Ray Air. You have the core Ray Air libraries, so like Ray Data, Train, Tune, and Serve, as well as the integrations that we talked about, right? So for like metrics and monitoring. On the training side, right, PyTorch, TensorFlow, Hugging Face, Horovod, scale all those easily on top of Ray clusters. And then finally, all the upstream and downstream parts, right? So like if you have your data in Delta Lake, you want to be able to easily take that data and move it into your training, into the training part of your ML pipeline. So that all has to be done very seamlessly. And with Ray Air, we don't require or force you to pick a particular framework, right? You can use the best of breed for each particular component and have that work very easily with Ray. So taking a look at some of these other libraries that are included with Ray Air, one of them is Ray datasets. So for distributed data ingestion, right? So given data that's stored in some external storage, you want to be able to read that data, do some last mile preprocessing, and then feed that data into your trainers in an efficient way. So with the Ray datasets, you can easily split your data across your training workers. You can window your data, so apply preprocessing only on windows of data in case your data does not fit, is larger than RAM. And one of the cool features that we enable here is pipelined execution, right? So while you're training on one batch of data, with the Ray Train, Ray datasets can be doing preprocessing on the next batch of data. So you're using GPUs for training, but at the same time, you're using CPUs to start preprocessing in the next batch. So you can keep your GPUs fully saturated by continuously feeding batches to them. So here's just an overview of like how our preprocessors work. With Ray Air, we have like some off-the-shelf preprocessors that are very similar to scikit-learn. So you basically use the same preprocessors that you would with sklearn, except swap them out with like the Ray Air preprocessors, and these will execute your preprocessing in a distributed fashion, enable the pipelining that we just talked about, and also very easy to implement your custom preprocessors. Another component here is about hyperparameter optimization. Ray Tune is one of the most popular libraries on Ray, and you can easily take your Torch trainer that we showed before, the distributed training component, and then put that into hyperparameter tuning. So what that means is that you basically specify a hyperparameter search space, and Ray Air will automatically launch multiple trials, each with a different hyperparameter configuration, where each hyperparameter configuration is also a distributed training job. So Ray basically abstracts away all of this complex resource management when it comes to like nesting distributed jobs within each other. And finally, once we have our trained model, we want to be able to do scalable offline and online inference. So once you've called trainer.fit, you can easily get a checkpoint from that trainer. You can pass it to our predictors that we provide in Ray Air, and then use that either for offline scoring. So if you have a distributed test data set that you want to do scoring on, you can use our batch predictor, which we're going to show later. Or if you want to do online inference, you can leverage Ray Serve. So basically deploy that predictor in a live setting to actually handle prediction requests. And one other important aspect of any ML application is monitoring and observability. So our trainers have integrations with TensorBoard, with MLflow, with other monitoring tools, so you can easily see how your training is doing during the distributed training process. So there's no extra setup you would have to do. Comes out of the box here. So even if you're running on a large cluster, the monitoring and observability components are very easy to enable. So let's just go through a quick demo here about the Ray Air APIs. We're going to show how you can, we're going to go through an example of how you can train a TensorFlow model on a multi-GPU cluster. Right, so you can start a cluster on Ray open source, but for this demo, I'm just using Anyscale that starts a cluster for us. You can see that we have 3 nodes in our cluster on the Ray dashboard. And total number of resources that we have 40 CPUs, and we have 2 GPUs. Okay, so we're gonna, let's get started with our training. So I can open a Jupyter notebook, and I can develop my entire ML application directly on this Jupyter notebook, even though when I'm using Ray, it can scale out across the entire cluster. So in this example, we're going to go through how you can load in data with the Ray datasets, process the data set using the Ray Air preprocessors, train the model with the TensorFlow trainer that we provide, and then finally test our model predictions using a batch predictor from Ray. So the first thing we do is we want to initialize Ray, and we see that it's able to correctly identify the resources across the entire cluster. So 40 CPUs, 2 GPUs. And the next thing we want to do is we want to load in our data, right? So we're just going to use Ray datasets for this. So in this example, I have the data just stored as CSV files on disk. You can easily use Ray datasets to read data from S3 or other data sources as well. So we're going to load in these data, load in the data in a parallel way with the Ray datasets. And then we get to the preprocessing. All right, so we have a bunch of built-in preprocessors to do the type of feature engineering or take your data and transform it into a way that can actually be used to train your model. So in this case, what we're going to do is we use a simple imputer to impute missing values in certain columns in our data. And then we also want to one-hot encode all the categorical columns, or all the categorical features. And finally, we implement a custom preprocessor to convert our trip start timestamp into a year. And we finally chain them all together into a single preprocessor. Cool, so we've loaded our data, we've defined our preprocessor. Now we just set a few configuration settings, right? So we have an input size of 128. Batch size of 16. Let's train for 2 epochs, and since we have 2 GPUs, let's use 2 workers. So now we get to the training, right? The training part, the code looks very similar to what you would use when running on your laptop or running a simple example, right? I have a function to build my TensorFlow model, and now I just define this training function, this train loop per worker. So this basically specifies the logic for training on a single worker, right? So each data parallel worker is going to be running this function that you define. What we do first is we get our dataset shard, right? So when we pass in the train dataset, as we talked about, it gets sharded across all of our workers. So we get the shard for this particular worker. We create our TensorFlow model and use TensorFlow's multi-worker mirrored strategy to distribute it. We prepare our dataset shard, and then we just do a model.fit. And then finally, at the very end, we create a checkpoint and report that checkpoint to Ray Air, so it can store that checkpoint, and we can load from it later. Once we've defined our training function, we can pass it into our TensorFlow trainer. So we pass in our train loop per worker, and then here's where we specify the scaling config, right? So I want to train on 2 workers, and I want to use GPUs. So this way, I can parallelize my training across my entire cluster and use both GPUs in my cluster. I also pass in the dataset, the trained dataset that we loaded in earlier, and then I also pass in the preprocessor that we defined earlier as well. And then finally, I call trainer.fit. So what happens when we call trainer.fit, this will preprocess your dataset using the preprocessors that we defined. We'll shard your dataset automatically, and we'll send each shard to the appropriate training worker. And then each training worker will run the function that you defined above. So each model replica will be training on its shard of data, we'll be synchronizing its weights, and then finally at the end we get a checkpoint out of this containing the trained model. So it's going to run for 2 epochs, and we see an accuracy of around 82%. So now let's say I want to go change my batch size, right? I'm not happy with this. This didn't really give me the best accuracy. Let's change my batch size and try it out again. Again, this is very, very easy to do. I just make the change to my cell. I just rerun these cells, and that's it. I can make one line of code change and now scale, once again, continue to scale across my entire cluster. So now I change the batch size and reran training here. Yep, and now we see that training is finished. And after that, what we can do is now once we've trained our model, we can now test it with our test data set and see how well it performs. All right, so the first thing we're going to do is just extract out the features and labels from our test data set. And then now I'm going to use this batch predictor that we've defined in ArrayAir. Right, so I can give it the checkpoint that was returned by our trainer, tell the batch predictor to use the TensorFlow predictor implementation, and then give it the model definition to create the TensorFlow model. And so I can call batch predictor.predict on my test data set, and this will do evaluation on my test data set, once again, scaling across the entire cluster and using the CPUs across the entire cluster. And finally, once I have my model predictions, I can then just calculate the scores, and we'll see we have a final accuracy, test accuracy of around 80%. Cool. OK, so just to recap, right? Why ArrayAir? Well, as you saw, it's very easy to use and iterate, right? Work entirely with Python, use notebook development, even though you're scaling across an entire cluster. You can make changes without having to shut down and restart your cluster, and makes your job as a model developer very easy. It abstracts away all of the infrastructure. So you don't have to worry about scheduling, resource management. All you do is change your scaling config, and then you can scale from single GPU to hundreds of GPUs. And it integrates really well when building a full end-to-end ML application. So how you can have scalable data ingest, scalable training, scalable inference, and prediction at the very end. So yeah, that's thank you for taking this talk. We'd be very happy to get in touch with anyone who's interested in trying out or has any questions. So if you're inclined to chat with us some more, we'll be hanging around a bit after this talk, or you can fill out this form and we'll be in touch with you. Thank you.
Are there any questions for our speakers?
Hi. Does RayServe address the large model file problem you spoke about early in the presentation?
Yeah, so there are current efforts in being able to support large models and serve those efficiently. Happy to chat with you afterwards. Some more details there.
Yeah, hello. So do you support something like DeepSpeed, Causal AI, Megatron, something like that?
Yeah, that's a really good question. Again, the answer there is that those are definitely easy to integrate with ArrayAir and the RayTrain libraries. And that's something that we've looked into as well for being able to train, again, very large models. So yeah, I'd say happy to chat with you afterwards, some more details there.
My question is, do we support any customized the model weighting aggregation? Because I suppose we are doing a data parallel to train a model, and so we need some way to aggregate the weights of the model, right?
Yeah, so the weight synchronization and the communication for the gradients, that's all actually being handled by either PyTorch or TensorFlow or Horovod. Right, so Ray itself doesn't claim, we don't have any special algorithms there. You can still continue to use the best libraries for efficient deep learning. But what we do what we do enable is a very easy user experience, abstracting away like the process orchestration. So you can continue to use the very optimized libraries for that have really good deep learning algorithms and very high performant, while also having a very easy to use API.
Any other questions? Awesome. Thank you.
Thank you.